greater than the median. So we're going to look at the relationship between the mean, the median, and the mode. If we look at a symmetrical bell-shaped distribution, which is one of those shapes we discussed in the last lecture, noting that on the horizontal axis you have your numbers, your data values in ascending order from left to right, and the height represents the frequency. Now over here we have small data values, over here we have large data values, and in the center we have something right in the middle. Now when you have a symmetrical bell-shaped distribution, the mean, the median, and the mode are all right at the center of the distribution, and they all have the exact same value when you're dealing with a bell-shaped distribution. So they're all in the center and they all have the same value. There are some values less than the mean, median, and mode. There are some values, data values, that are greater than the mean, median, and mode. The mean, median, and mode is directly in the center. Okay, if we look at a skewed left distribution, here's a picture of skewed left. And remember from our last lecture, skewed left means that the tail is being pulled out towards the left. The mean and the median have smaller values than the mode, as they are influenced by the extreme small data values that occur in the left tail of the distribution. So here's what happens in a skewed left distribution. The mode contains the data value that appears with greatest frequency. So the highest frequency, noting that frequency is the vertical measure right here, the highest point of this graph represents the mode. So that's easy to spot. Now what happens in a distribution if you have a lot of small data, or I'm sorry, most of your data values are occurring in this range, but then you've got some really small data values down over here. So imagine a distribution of incomes where most of the incomes were over $100,000, and then you had a few incomes that were in the teens and 20s. Now what would happen to your mean because you have data values in the teens and 20s? Well, the mean would be brought down. Notice that here's the mode. The mean is going to be pulled out to the left because it's going to be made smaller because of these small data values down here that are basically dragging it to the left. The median is also going to be pulled somewhat to the left, but not as far to the left as the mean. The mean is really pulled lower because of these low data values. Consider the calculation of, imagine your test score, imagine test scores that are all in the 80s, and then you get a test score in the 20s. Well, your mean test score is going to be pulled down lower because you've got that 120, and that's what's happening here. You've got low data values, which makes it a skewed left distribution, and those low data values pull the mean down towards the left, and it does skew the median slightly as well. Okay. The median is larger than the mean because the median is not influenced as greatly as the mean to the extreme small values in the left tail. Okay, let's look at the exact opposite, the skewed right distribution. The mean and the median have larger values than the mode. Okay, so here we go again, looking at a distribution where numbers are listed in ascending order from left to right. And again, the mode is the data value that's got the greatest frequency. So the highest peak of this distribution represents the mode. Now, the mean and the median are both larger than the mode, because they are influenced by large data values that occur in the right tail. So here we have the right tail, and in a skewed right distribution, the reason why it's called skewed right is because there are a few data values up here that are pulling the distribution, pulling the tail to the right. So you can imagine a distribution of test scores in the 70s, and then you get a test score of 100, which has the effect of pulling the distribution to the right. Okay, because of that test score of 100, the mean is inflated, right? Imagine you're adding up 5 test grades, all of which are 70, but the last one is 100. You're going to have an inflated mean. It's going to be greater than the other data values, the 70s, because of the calculation involving the 100. The median is less than the mean because the median is not influenced as greatly as the mean to the extreme large values in the right tail. The median is still greater than the mode because it's pulled to the right somewhat, but not as greatly as the mean. The mean is more greatly affected when you have data values in the right tail. Okay, the mean is not a resistant measure of central tendency as it is not resistant to the influence of extreme values of outliers. So we saw in these two examples that you can have a skewed left and skewed right distribution, and the mean is greatly affected by data values in the left or right tail. So imagine that you have a few very high incomes in a distribution where most of the incomes are low. Well, those few very high incomes are going to have a great influence on the mean, even if most of the data values are lower. The median is more resistant than the mean, as its value is not significantly influenced by extreme data values, which can be considered outliers, regardless of how large they may be. So you can have a few large data values in the distribution. The median is not going to be affected as much as the mean will be. Okay, the mode is the most resistant measure of central tendency to outliers. So when we say outliers here, in this example, when you consider incomes as outliers, if most of your distribution is full of low incomes, and then you have a few numbers in the 200,000, 300,000 range, those numbers would be outliers. And the mode, though, is not really affected by those outliers because the mode is still the point of highest frequency, the number of greatest frequency. And since you only have a few of those extremely high incomes, they are not going to be the mode. Okay, so that was the mean, the median.